Welcome back to another piano tuning myth video. In this video you're going to get two for the price of one. Piano tuning myth 5, which says that you must keep the hammer at 12 o'clock for the best stability, and piano tuning myth number 10. You must go sharp and ease the pitch down for the best stability. Well, let's start by just talking about the parts of the piano. We got the pin block, we have a tuning pin. This is an upper termination point where the string touches. The string is wrapped around the pin, goes over to this termination point, and the string between the tuning pin and the upper termination point is called the non-speaking length. And where the string is vibrating, we call that the speaking length. So here's a top view of this. We've got the pin block, tuning pins, there's the strings, there's the upper termination point, and the non-speaking length above the upper termination point and the speaking lengths below the upper termination point. Many people say you have to keep your hammer at 12 o'clock. What does that mean? Well, just like you see here, it's at 12 o'clock and you move the handle side to side. And along with this instruction comes another instruction that says you should go sharp a little bit of the target pitch and then ease it back down for the best stability. An example would be you come to a piano, the pitch is flat, so you tighten up the string, tighten it up until it's a little bit sharp, and then ease it back down. And that's supposed to give you the best stability. But why do people say this is the best way to get good stability? Let's look at the tuning pin here. You see that there's a little arrow counterclockwise. That shows the force that the string has on the pin. The string is always trying to twist the pin counterclockwise. So the fact that we made a counterclockwise motion as our last motion makes us feel confident that the pin isn't going to twist on its own in that direction under the tension of the string. Also, let's take a look at this tuning pin as we apply a force to it. Notice that the static picture of the pin, which is not moving, clearly shows that when we try to turn the pin, it's actually bending perpendicular to the handle. Visually, we can show this where we take the handle and we turn it to the left, and you can see that the pin is bending a bit, right? And then we go to the right, same thing, pin is bending. But what's happening to the non-speaking length tension when we do this? Well, you can imagine, like I'm exaggerating this, but yes, I suppose that the string is stretched a tiny bit. Actually, it's not much at all. The bending of the pin when the hammer is at 12 o'clock has virtually no effect on the non-speaking length tension. However, if we put the hammer at 3 or 9 o'clock and we start trying to turn the pin, we can see that the bending of the pin is parallel to the string. So when we try to turn the pin counterclockwise, we push up on the handle and it's pushing up on the pin, and that's stretching the non-speaking length tension. So that's a huge difference in non-speaking length tension. Bending parallel to the string produces the most change in non-speaking length tension. And this produces a piano tuning truth, which is that the tuning hammer at 12 o'clock has a minimal effect on the non-speaking length tension. And when the tuning hammer is at 3 or 9 o'clock, it has a maximum effect on the non-speaking length tension. But if putting your hammer at 12 o'clock gives the best stability, presumably because there is a minimal change in the non-speaking length tension during the tuning, then why does this happen? That's a drop of 10 cents. What's happening? In order to answer that question, we need to know why and when the go sharp, ease flat technique works. And in order to understand that, we need to discuss twisting of the tuning pin. Look at this tuning pin. As I try to turn it, you can see that the X is twisting, and then when I remove the force on the tuning hammer, it bounces back to where it was before. So we have twisting and untwisting happening here. Twisting when I pull, untwisting when I let go. If we look at the non-speaking length tension under the twisting effect, we can see that as we apply the force, the pin starts to twist, the tension goes up, and then when we remove the force, the pin untwists by itself, and that lowers the non-speaking length tension a tiny bit. Watch that again. The red arrow is high. When we remove the force, the tension goes down a bit because the pin untwists by itself. Going the other way, we apply the force to the left, the non-speaking length tension drops, and then when we remove the force, the pin untwists by itself, and that causes the tension in the non-speaking length to increase. When does this technique go sharp, ease flat work? Well, we're starting out here with the pitch flat. What we do is we raise the pitch until it's sharp of the target, and then we ease the pitch down, and the non-speaking length tension is getting flabby now because we're loosening it. And when we get to the target pitch, notice that the non-speaking length tension is now low. It's flabby. That's because of friction at the V-bar. What are we going to do? No worries. We haven't removed the hammer force yet. Watch what happens when we remove the hammer force. Without doing anything, just by taking our hammer off the pin, it untwists and the non-speaking length tension increases. Watch that again. Watch as I do it on the piano. So this technique does not always work. In that video you saw that it did work. Why doesn't this technique work all the time? Well, let's look at our situation where we have the flat pitch and we raise the pitch until it's slightly sharp. Then we ease the pitch down. And remember, as we're easing the pitch down, that non-speaking length is getting flabby. And then the target pitch is reached, and the non-speaking length tension is too low. We know the pin will untwist when we remove the force, but in this case, it untwists and the non-speaking length tension increases, but not enough. The non-speaking length tension in this situation is too flabby, and on the first hard blow, the string slips, the non-speaking length tension rises, and the pitch drops. Watch that again. On a hard blow, it goes flat. So what can we do about this? Well, the Go Ape Aural Piano Tuning System teaches a method of knowing exactly how to get good stability by leaving the non-speaking length tension tight. You'll know how much the non-speaking length tension has changed, and you can change your hammer technique to increase the non-speaking length tension if it's not stable. And also, you can get stability with very few test blows, if any, by using this method. I wanted to show you some of these myths that people follow when they're tuning a piano, and the issue with these myths is not that they don't work, it's just that they don't work all the time. With the Go Ape Aural Piano Tuning System, you're going to be taught a method that works all the time, and if it doesn't work, you'll know what to do to make it work without having to use heavy, damaging test blows.